So I'm here to present the development of a Python library that we created, we developed for post-processing and imaging with ultrasonic data. And the main motivation for that is in our team, in our research team, roughly 25 researchers are currently working with ultrasonics applied to NDT. We also have a huge project with Petrobras, the Brazilian oil company. This project has many research fronts, all of them involving ultrasonics for NDT of subsea inspections. So we needed a standardized software, a standardized set of procedures for ultrasonic data processing. Avoidance of rework, so we don't want that. Many people do the same thing over and over again. And in 2018, we started the development. Since we are working mainly with subsea inspections, we needed immersion testing algorithms. So we developed adaptive reconstruction algorithms. So for instance, the adaptive TFM, which is the TFM ready for many layers of different materials. We needed surface identification methods. We needed it to be NumPy powered because NumPy is free and is widely used in the research community. We needed to implement state-of-the-art reconstruction algorithms with flexibility for parameterization and easy for adaptation and addition of new features. All of that requires professional level repository management because it's a lot of information, a lot of people working in the same software project. So we began to implement all of this in 2018. Another thing that was and is important for us is standardization of the representation of ultrasonic data acquired from different equipment. Back then we had a Panther, an Olympus Omniscan. Now we also have a Pioneer. We had since 2019 a license of the SIVA simulator. So we needed all of these data to be represented in the same manner so that the same algorithms could be called to process those data.
O Gecko não está também? Desculpa. Ele não entrou também?
O Gecko... Pois é, como é que está... É que eu não tenho certeza de como é que está o andamento da... Quão pronto está o Gecko, se foi só para aquele conjunto de dados ali.
Está feito todo o conjunto de dados, mas o Giovanni, eu não sei como que ele está desenvolvendo a leitura, se já está avançado.
Depois daqueles testes, a gente não avançou em deixar redondinho, né, para colocar na biblioteca aqui.
Tá, beleza.
Mas a gente lê do Gecko também. In 2019, we published our first paper on our toolbox of ultrasonic procedures and algorithms in QNDE, because in 2019 there was ECNDT, unfortunately, because ECNDT happens every 3 years. So 2019 we went to QNDE to publish these first results. The toolbox was not yet publicly available. It was only used inside our research group, but we have a very good feedback. Many people were interested in testing and applying it to their research projects. So we started to create a Python library which was meant to be publicly available. So now I'm going to show some papers that we published using that toolbox before the creation of the library. So there is this image-based ultrasound speed estimation method which used the TFM implementation and used the procedures for reading data from Panther. The surface identification method that we published in 2021 also used our set of procedures. This paper from the last ECNDT, where we did imaging with temperature gradients that translate into velocity speed gradients, was also implemented using our toolbox. Our directivity assessment method was also implemented using our toolbox. This one used data from Olympus, Omniscan, and the Panther. In the paper, only the Panther in the paper? Or?
Yes.
Okay. But in your thesis, there are data from Olympus?
No.
No. So take some notes. don't reproduce my errors. Then in 2024, we published this web application called the mini-auspex, and the goal was to make our toolbox available for anyone to use. But here, mini-auspex, which is our library, was already deployed. It was used here in this PyODide application, but a specific paper about the library was lacking. So now in the ECNDT 2026, we are publishing this paper, which is the one that you're going to cite when you use our toolbox. So since then, we continued publishing new research using now the mini-auspex library. One very interesting is our acoustic lens method that uses a surface especially designed for to create the refractions necessary to make perpendicular wavefronts over the pipes. In this conference, apart from this paper, we have also 5 other papers. All of them were produced using the mini-auspex toolbox. So it has been very prolific inside our research group. So how it is structured, it's a quite simple and quite short structure. There is the framework, and here the main groups that you're going to use is file Siva to retrieve data created by the Siva simulator, and file M2K to retrieve data acquired by Panther. Data from the Olympus and Omniscan is not comprised in this version of the library because it needs some local DLLs that were impossible to make available in the repository. So here we are restrained to Siva and M2K. Then there are the state-of-the-art delay and sum imaging algorithms, surface identification. We had to create a package for our own package for nonlinear optimization to implement Newton's method inside our surface identification procedures. So it's also available for whoever wants to use them. And finally, the parameter estimation. So estimation of sound speed in the material and estimation of internal surface. And then I'm going to show you a live example on Google Colab. This is a setup that we created for this example. We used immersion testing because we think that it's a more complete example. So what happens here? The Panther system acquired the data. So our procedures for retrieving data load the data to the memory. Then we run the surface identification procedure to find the surface. Then we create a region of interest using our the region of interest class, which is comprised in our library. And finally, we do the immersion total focusing method and create this image that is going to be displaced. So I created a video. We can play it here. So rolling down a bit. Since Google Colab doesn't have natively our library, we have to pip install it, but it takes a couple of seconds. It's a very easy process. Then we will load the data. I hosted the data in Google Drive, so I'm using GDown to load it. So data is loaded in the virtual file system here in Google Colab. And now we are good. You are going to use file M2K to load the data into our standard form of representation. So the data is already loaded. It is represented in this class, data inspection class. We call it the data inst object. So here I just plotted a B scan and the first A scan, so just to show how what a set of data looks like. So what the script is going to do next is to identify the surface. So we have this surface class. I create an object of this type, and I ask it to fit a surface from the data. And here I've chosen it to be a line because I know that the surface is flat. So I ask it to find the best line. Then I'm going to plot the surface here, even before the image, just to do a previous check. So this is the surface that our toolbox found. These are the locations of the transducer elements. Now we create a region of interest. Our region of interest object is created in this manner. We pass the location of the top left corner, and then the height, width, number of pixels in each of the 2 dimensions, and it creates the arrays. I'm going to plot now the region of interest. Here's a point for each pixel with the same other features that were present in the previous image. And now finally the TFM. So I just call TFM, the TFM kernel from our library, passing the data, the region of interest. I'm asking for analytic signal to do the demodulation of the RF ultrasonic data. And voila, I get a TFM image, which is going to be shown in the next cell. So running the last cell, we see the resulting image. And here I plotted all the other features just to locate the image, to locate the features, the image in the setup. So it's as simple as that, the pipeline of procedures for doing an immersion TFM with our toolbox. And the use of the other methods are just as simple. So in the paper, there's a link for a GitHub repository where you find this example and other examples with CPWC, with SAFT, and so on. Coming soon, we're going to add to our library the procedures for project and assessment of resolution of our acoustic lens. So you can do different parameterization and see how it behaves. There will be a small simulator for assessing spatial resolution, and also the focal law, the computation of focal laws, because there's a very complex method of focal laws that allows this setup to work well. And as a conclusion, we created this free NumPy-based ultrasound data processing library. It has been very useful and very prolific inside our group, and we hope that it will help other groups of researchers. So please try it, cite it. Now you have the paper, the right paper to cite. Do your pip install mini-auspex, and then we will appreciate any feedback with suggestions, maybe with requests of new features, and bug reporting would also be very appreciated. We thank our dear university, Petrobras, UTFPR, the financer of this, the funder of this project, Petrobras, the Brazilian Oil Agency, which has another funding project in our university called the PRH, Fundação Araucária, and CAPES. So thank you.